Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the types of electronic transition and what type of the main type of the electronic transition, what kind of the organic molecule exhibit what kind of the transition. Generally there are four types of transition. Number one, sigma to sigma star transition. Sigma to sigma star transition generally shown by the organic molecule which are saturated. There is no saturated the molecule like methane, ethane, propane, butane, hexane and so on. Another one or the second important transition state will be pi to pi star transition state, and pi to pi star transition state will be observed in the organic compound which are unsaturated in nature, means containing as a multiple bond, carbon-carbon double bond. Examples of this type are alkenes, like this. And third type is a N2 sigma star transition. What type of the organic molecule will show this type of the transition? Generally those organic molecule saturated organic compound containing heteroatoms such as alcohol, amines, halides, thiols, etc. can exhibit such type of the transition. And the last one and the one more prominent transition is the N2 pi star, N2 pi star non-bonding, and the pi star will be observed in the organic compound which containing multiple bond with heteroatoms such as carbonyl compound can be show such type of the transition. Now today what we are going to discuss, let's look at the board the terms used in UV spectroscopy. Let me tell terms used in UV spectroscopy means important terms involve or utilize or use in a UV spectroscopy. Few of the terms which are the prominent term used in the UV spectroscopy, they have significant role in UV spectroscopy, and that's why we are going to study one by one with their example, and we will try to understand the concept with the suitable example. Let me write here the first important term, which is chromophore. Which is chromophore. Here, listen the definition of the chromophore carefully. It is isolated functional group capable of absorbing UV radiation. We call this group as the chromophore. It is a Greek meaning chroma means color and phorus means bearing. Some important chromophores are like this: NO2, then N double bond O, then C double bond C, then C double bond O, C double bond S, then N double bond N, etc. These are the group, these are the example of chromophores. According to the definition, these are the isolated functional group responsible for absorptions of UV radiation, and therefore such type of group are called as chromophores. Understood this? Chromophore is nothing but it is isolated functional group capable of absorbing UV radiation with WI T is known as WIT, is a scientist name. He discovered these terms, and we generally using these words, and that's why chromophore is a isolated functional group capable of absorbing UV radiation is known as chromophores. And the examples are written on the blackboard. You can see clearly and you can remember, even though this forever in your life. So second important term generally used in the UV spectrophoto spectroscopy is this one, auxochromes. Auxochromes is another important term used in UV spectroscopy. Now let us define it. How do we define it, or how do we describe it? Let's see. It is a functional group which itself does not absorb radiation in near UV region, but when attached to a chromophore, shift the absorption to a longer wavelength. Some of the auxochromes are OH, OH3, NH2, etc. These are the examples are given. Once again, remember as auxochromes. Auxochrome is one of the important term used in UV spectroscopy. It is a functional group. It is a functional group which does not absorb UV radiation alone. but when it attached to a chromophore, shift the absorption to the longer wavelength is known as exochromes, and some of the examples of that exochromes are this one OH, then OH, CS3 or NH2, etc., etc. Now, these are the functional group, no doubt about it. This is alcoholic, this is a ester type, and that will be the amine. But these individual groups, isolated functional group, these do not absorb UV radiation, but when it attached to the chromophore, such as benzene, the shift the absorption to a longer wavelength. Let's see over here. You know that the structure of benzene is this one. Benzene containing as a carbon-carbon double bond. It means it is a chromophore, and the characteristic of that benzene, it shows the peak or the bands or the signal around 255 nanometer. 255 nanometer peak observed or seen in the UV spectrum. From that we can easily identify by observing the spectra carefully. We can identify what type of the organic compound present there. So 255 nanometer peak or the signal or the band is corresponding to benzene moiety. And now we have another structure. Look at this structure. What I did here, benzene, one of the hydrogen atom, I have replaced with this group. And now let me draw another structure. Here also I have replaced another hydroxy group by methoxy, and now I am circling it. See this one, these two are nothing but as a oxochrome. These two are oxochrome. And now if you see its lambda max, the peak. So just you tell me here, if benzene is present, it produces or it gives the peak around 255 nanometer. Now you just tell me the peak due to the phenol will be greater than this or less than this. So according to the definition, it is a functional group which does not absorb UV radiation, but when it attached to chromophore, shift absorption to the longer wavelength is known as a oxochrome, and in accordance with this definition or the rule, we can definitely say that lambda max will be, or lambda max always greater than this one, so it will come around 265 nanometer. Now if you see over here, benzene, as we know that 255, that is a constant, but there is a increment, there is a addition of lambda values due to the presence of these presence of exochromes, and therefore in this case lambda max will be observed at 270 nanometer. That are the rough approximate values, that is not the exactly value, because as we know that UV spectroscopy provide us the information regarding the structure of the molecule which contains, or that contains carbon-carbon double bond, then dienes, trines, etc. It also provides us the information about isolated, conjugated system and diene conjugated system, diene and trine, carbonyl group and alpha beta unsaturated compound. It also provides the information about stereochemistry of the molecule, like geometrical isomers. From UV spectroscopy we can easily distinguish between cis and trans isomer by observing its peak, by observing its signal. Cis isomer observe at lower wavelength as compared to the trans, or in another way we can say trans isomer absorbs at longer wavelength. So this is another term used in UV spectroscopy. Now let us move on to the third point, that is bathochromic shift or red shift. Third one we can say here, third one is a bathochromic shift or red shift. Third one is known as a bathochromic shift. Bathochromic shift, or which is known as red shift. How do we define bathochromic shift or red shift? See here, absorption to a longer wavelength is known as bathochromic shift or red shift. For example, para-nitrophenol shows red shift in alkaline medium. For example, para-nitrophenol shows red shift in alkaline medium. The medium 2 or 3 mark question may appear. The nature of question is like this. Explain the following. So here para-nitrophenol shows red shift in alkaline medium. They will say explain. So how will you explain or how will you answer such type of the questions? So first of all, you are the organic student, so you must know the structure of the organic compound. Once you able to draw the structure of organic compound, your half work is done here. So that is a very essential or prominent requirement for answering such type of questions. So I hope majority of you are knowing the structure of para-nitrophenol. See here, this, if you observe the structure carefully, you will see here is a benzene. Phenol means one of the hydrogen atom replaced by hydroxyl group, so which is a phenol. Now P, at what position nitro group is attached, that position, as we know that this is a phenol, adjacent two positions are ortho position. These two positions are meta position, and exactly opposite to this substituent is a para position, and therefore at this position you can show that nitro group. Generally NO2 we are writing here, and this is the way of representing nitro group here. For this is the structure of para nitrophenol. Now alkaline medium. Alkaline medium, it means whether it is acidic medium or basic medium. Alkaline means basic medium. Very good. Now you can generally sodium hydroxide or potassium hydroxide is the basis. Do you remember in some examples only OH minus are written? OH minus is nothing but that hydroxyl groups are coming from either from sodium hydroxide or potassium hydroxide or other alkali metals or barium hydroxide or aluminum hydroxide. And now what is the function of that base? It will abstract the acidic proton, and the proton which are attached to the oxygen atom are acidic in nature. When it abstract the proton, it leaving the bonding pair behind, and so we will get the resulting compound like this, that is O minus phenoxide ion. And as we know that phenoxide ion are well stabilized, and due to that reason that hydrogens are acidic in nature. Now in this case, if you show this lone pair, it coming down, and there is double bond shifted from here to here, there is double bond shifted from here to here, and the negative charge resting on oxygen atom, if you see the length the chromophoric, that is called as a chromophore length. As the chromophore length goes on increasing, the wavelength also goes on increasing. And if you see the lone pair which is present on oxygen atom, is there no doubt about it, it is also capable of donating, but the donating ability is less as compared to the oxygen atom which carries negative charge. The negative charge has more tendency to donate the electron density than the oxygen atom which is along with hydrogen atom. So these are the things we have seen with the help of this example. Now move on to the next point. Next point we are going to discuss fourth important term used in UV spectroscopy, that is the name of that fourth term is hypsochromic shift. Hypsochromic shift, it is also known as blue shift. It is also known as blue shift. If you remember, previous one we have seen bathochromic shift and the hypsochromic shift, they are against to each other, means they are opposite to each other. In previous case, while defining as a bathochromic shift or red shift, we defined it as an absorption to a longer wavelength is known as bathochromic shift or red shift. Here, hypsochromic shift or blue shift is nothing but an absorption to a shorter wavelength is known as hypsochromic shift or blue shift. And now here 2 mark question may appear on this point. So what that, let us see here. The aniline shows blue shift in acidic medium. For example, aniline shows blue shift in acidic medium and explain. So that becomes as a question. And how do you explain this type of the question? Remember here once again, hypsochromic shift or blue shift is nothing but an absorption to a shorter wavelength is known as hypsochromic shift. And here aniline shows blue shift in acidic medium. As we know that the structure of aniline, and it is important to know the structure of aniline, otherwise it's very difficult to answer such type of the questions. Now look at here, benzene, as we know that it is a chromophore, and where this is oxochrome present on it. So the lambda max, the characteristic peak of benzene, as we know that 255 nanometer. Now when oxochrome attached, it increases or decreases? It increases, so it is found to be 260 nanometer, let's say here. And now when it is treated with HCl, which is acid base reaction, the resulting compound form will be the salt, and you may get here this type of the compound. Here NH3 positive charge and Cl will be the minus charge. Now here what is happening, the lone pair which is present on that nitrogen atom here readily available for donation, or it is involved in the delocalization. There is a increase in the chromophore absorption occur at or shift at a longer wavelength. But in this case, that lone pair is prohibited, or what we can call it as it is banned, and therefore it is not available over there. It forms as a salt, and due to this reason, the wavelength is, you tell me, the lambda max we observed here is a 260 nanometer. Now tell me whether it is the lambda max is found to be, or lambda max was found to be greater than 260 or less than 260. It should be less than 260, so it found to be here you can remember as a 270 nanometer, here 265 nanometer. You just for the clarity to understand the basic thing regarding that, and that's why you can show this type of the values, because it should show as a greater value lambda max, and this will be the less. So that's the reason. So these are the 4 terms we have seen so far. Now the next point which we are going to learn, 5th point, will be this one. Let us see here. 5th point will be the 5th important term using is a hyperchromic shift. 5th one is a hyperchromic shift. Hyperchromic shift. What does it mean? How do we define it? When intensity of absorption increases, it is known as hyperchromic shift. It is related to as a intensity. Hyper itself, hyper means high intensity, means when intensity of absorption increases, it is known as hyperchromic shift. And the one more term is a hypochromic shift. And 6th one is a hypochromic shift. And hypochromic shift and the hyperchromic shift, they are exactly opposite to each other. When the intensity of absorption decreases, it is known as hypochromic shift. So these are the important terms which we have learned here as far as this UV spectroscopy is concerned. So now let me tell one more question is generally appear in the exam. The question may be like this: how will you distinguish? Question is the nature of question like this: how will you distinguish following pairs by UV spectroscopy. How will you distinguish the following pair by UV spectroscopy? And the pairs are given. One, suppose as a CH2 double bond CH and CH2 double bond CH double bond CH2. But if you observe or it may be like this: CH2 double bond CH, then CH2, then CH double bond CH2, not, here is a CH2. This is known as ethylene, as we know that, ethylene, right? And this is known as 1, 2, 3, 4, that is a diene system, that is 1, 3, butadiene, butadiene. And if you see this one, 1, 2, 3, 4, 5, it is known as 1, 4, 1, 4 pentadiene, pentadiene. Now, if you observe these three structures carefully, how do you distinguish this? By UV spectroscopy. And you remember, if carbon-carbon single, carbon-carbon, this one CH2 ethylene, it is for UV. It cannot be recorded or measured in UV spectrophotometer, ordinary spectrophotometer, which is made up of by the wavelength is a 200 to 400 nanometer. And now this type of the compound you cannot but far away, but here it can absorb at it can show the lambda max is 165 nanometer, which is a characteristic of isolated system. Now this becomes this is a conjugated system, conjugated system, this one, or it is known as a diene system. It is known as a diene system, and diene system is stabilized due to the resonance. So the lambda max was found to be, for diene system, base value is lambda max was found to be 250 nanometer, this one. And now if you look at 1,4 pentadiene, the lambda max will be appear around, or was found to be 165 nanometer. Once again, we cannot distinguish these two molecules, one and third molecule, we cannot distinguish by UV spectroscopy, because both are the isolated system and both will produce the signal at 165, and therefore we cannot distinguish it from each other. But diene system, or it is a conjugated system, we can easily giving the band appear around 165 nanometer, and one diene system will produce the band around 215 nanometer. So in this way we can easily distinguish these two pairs from each other. So I think these are some of the important points regarding that UV spectroscopy we have learned systematically. So remaining in the tomorrow's lecture, we are going to solve the problem based on UV spectroscopy, how to solve it, which rule we should apply while solving that problems, that we will see the next lecture, tomorrow's lecture. Let us stop today here. Have a nice day. Thank you.